Okay, doing something a little bit different today. I wanted to do all the problems, all the integrals on the SwinBee 2022. There's going to be 18 problems. I'm going to move a little quicker than I usually do. Maybe not do out every step, just so I can try to get through it. So just to get started with this first, for this problem number 1, we've got here e as the constant. E is a constant as the exponent, so what we can do is basically just do power rule on this. You could do a u substitution on this, but we're just going to kind of do it in our head here. So to do this with power rule, we just do this kind of in one step. We'll bring back everything here, 7x plus square root of 2, add 1 to the exponent, divide by the exponent. But again, because we're doing the u substitution in our head, we'll just bring out this 7 in the numerator, so we'll write it as 7 times e plus 1 there, plus c, and that's it. Okay, moving on to question 2. That one was pretty easy. That was a really easy start. There's a lot of easy questions on here, so it's gonna keep it moving for me. So number 2, there's a few trickier ones, but a lot of them are kind of routine. So this one's just going to be the integral of cosine cubed x dx. Okay, what I can do here is actually break up cosine cubed. I can write this as cosine squared x times cosine x, just trying to set up a u substitution. And then what we'll do is with cosine squared x, whenever you write this, I can write this as 1 minus sine squared x. And then we'll have this cosine x here. Now we'll just do a quick u substitution, setting u equal to sine. Du is going to be cosine x dx, which we have right here. So this reduces to 1 minus u squared du. Integrated, what's going to happen? We end up with u minus u cubed over 3. Do the back substitution on this. Then we're going to end up with, for a solution, sine x minus sine cubed x over 3 plus c, and there it is. I'll have to check it. I think they have 45 minutes to do that. I think I can do it in 45 minutes. I don't know. We'll see what happens. Not sure. So going on to number 3, I guess there's some extra time just writing down all the problems. But anyway, number 3, we have here the integral of 2x plus 3 over x minus 1 squared dx. See, now there's a garbage truck outside. That could slow us down. I don't know if I'm going to have to stop the video or maybe they can empty the garbage quietly. Not really sure. So anyway, on this one, let's try not to get distracted. What I want to do here is, this looks like a good case where I can set it up and kind of force a cancellation. So if I just rewrite this as 2x minus 2, then this is going to be the same thing as 2 times x minus 1. But then if I had a minus 2 there and we have a plus 3, I need to add a plus 5, and we'll create that over here in a second integral. So here we'll have this x minus 1 squared. Then for the second one, we'll have this same denominator, x minus 1 squared dx. Now here in this first integral, this is going to cancel with one of these. So this first piece is just going to become 2 natural log absolute value x minus 1. And then here we can just do power rule, but a minus sign is going to come out. So we can look at this. We can look at this as x minus 1 to the minus 2. So if you do power rule, you get raises to the minus 1, divide by minus 1, we get minus 5 over x minus 1, add a plus c, and that's it. Now I'm starting to think if I do 18 problems, I don't need to say that's it every single time. So maybe I'll find a different way. So on to problem number 4, and see if I have some papers. Okay, so number 4, we've got the integral of the square root of x, and then we've got a nested cube root of x, and a nested 4th root of x, and this is going to go on and on like this forever. And so what I want to do for this is kind of rewrite it to see what's happening. So like the whole thing, for the outer square root here, I want the whole thing to be inside half power. And then within this, we'll have another one. This one's going to be to the 1/3 power. And then it's kind of confusing to look at. Then this one's going to be to the 1/4. And it's just going to be nested like this. It's kind of weird to think of it as being nested to infinity, but there's like an infinite number of terms in here. But then we can start kind of breaking this up a little bit and making sense of it. It's like just starting with this first x. This first x is only within this 1/2 power, so the first term is just going to be x to the 1/2. And then for this second one right here, this one's going to be to the 1/2, but we also have to multiply. If we distribute in with exponent properties, if we distribute in a 1/3, then the second one's going to be x to the 1/6. Continuing that way, the third way is the third x here is going to be 1/2 times 1/3 times 1/4. That's actually going to be, what I should do is do it as a factorial. That's going to be 1/4 factorial. And this is going to go on and on like this forever, of course. But then when we multiply these together, what we want to do is we just want to add all the exponents, so we'll have this. So what's going to happen is the integral is just going to be 1x with this giant exponent here. And so what we really need to know here is what is the sum of 1/2 factorial plus 1/3 factorial plus 1/4 factorial, on and on to infinity. Well, it turns out if I just create a couple more terms in front here, if I create 1/1 factorial and a 1 here, this is actually the power series for e to the 1, just because because for the power series of e to the x, because for the power series for e to the x, we'd have these x terms here in the numerator, but they're just all going to 1. So it kind of simplifies it down like this. So what we have here, I just made these terms up. So what we have here is not e to the 1, it's e to the 1 minus these first two terms, so e to the 1 minus 2. So what I can do is actually clean this whole thing up and then just reduce this exponent to e minus 2. We can drop the e to the 1. And so this is actually just going to be power roll because that's a constant value. So doing this, we're going to end up with x to e minus 1 over e minus 1 plus c, and that's it. Okay, that was a good one. Oh, I still said that's it. I need to stop doing that. So I need to just be like, done. Deal with it. That one's over. Or something. I need like a new catchphrase between problems if I'm going to do a bunch of problems. So, oh shoot, my paper. So moving on here, number 5. Let's see what that is. So problem number 5, we've got the integral of natural log 1 plus x squared dx. And I think for this, we'll just use integration by parts. That's often what you want to do for natural logs. So we'll do integration by parts, DI method over here, just differentiating the whole thing, kind of creating a 1 to integrate, right? So then let's just go ahead with this. Integral over here, x, derivative, 1 over 1 plus x squared, chain rule derivative of this gives me 2x. Then here on the diagonals, that's part of the solution, right? So x, natural log 1 plus x squared. Then here, this is going to be an integral, so I think I'll take the 2 out front, I don't know. So we'll have a 2 out front, minus 2x squared, 1 plus x squared. I think what I can do is let's add a 1, so then this becomes 1. I don't want to change it, so I subtract a 1, distribute it to the minus 2. That's going to give me another integral here, which is going to be plus 2 dx, x squared plus 1. So then we get 2 easy integrals here at the end. What's going to happen is we'll bring this down, x natural log 1 plus x squared. This again is 1, so we integrate here, we have a minus 2x, and then this is just going to be arctan, so we'll have a plus 2 arctan x squared plus 1, add a plus c, and circle it. And I think I need a new pen. Hold on a second. Oh yeah, I definitely made a mistake here. This is just supposed to be arctan of x, so let me clean that up. This is just going to be arctan of x here. We'll add a plus c, and we'll move on to number 6. So for number 6, I think this one's a messy one. Even though it's not hard, I think there's going to be some trouble simplifying it. Let's see. So number 6, we have the integral from 0 to pi over 4 with a new pen, sine cubed x over cube root of cosine x dx. Interesting. I think I definitely want a u substitution here because we've got cosine here. If I break this up in the numerator, if I break up sine cubed, right, we make this sine squared, and we write this sine x, we still have sine cubed there. Derivative of cosine is going to be minus sine x. So I'll create that to set that up there, and I'll bring a minus sign out front. So then let's just do this where we have u substitution for cosine x. du is going to be this minus sine x dx. Now, one thing I should mention before I do this, let's make this sine squared 1 minus cosine squared x just to set this up. So come over here, plugging in pi over 4. Cosine pi over 4 is 1 over square root of 2. Plug in a 0. Cosine 0 is just 1. Then with this 1 minus cosine squared, here in the numerator we're going to have 1 minus u squared du cube root of cosine cube root of u. I'll write that as u to the 1/3. Then I'll just use this minus sign and use it to flip the bounds, just so we have 1 over square root of 2 is something like 0.707. It's less than 1, so we like to have the, we don't really need to do this, but we like having the lower bound be the lower number for some reason. So then before I integrate, I'll just divide in the u 1/3 and rewrite this. So we're going to have this stuff. This first integral is going to become u. Actually, I'll just leave it in one integral. So we'll have u minus 1/3, and this is going to become plus u 5/3. Just thinking of 2 as 6 over 3. And sorry, this should be a minus sign right here. Mistake. du. Integrate this with power rule, and what's going to happen, we're going to have u 2/3. Then flip this, we have 3/2 here. Then minus power rule here, u 8 over 3. Reciprocal 3/8. And this is going to be evaluated from 1 over square root of 2 to 1. Now at 1, that's easy because we're just plugging in 1, so of course that's easy. So this is going to be 3/2 minus 3/8 for the first piece. Then here, let me try to simplify this a little bit first. So if I can write u to the 2/3 as u squared to the 1/3, and then for this one, let's try to write it as u squared. Should I factor it first? So this is where I get confused because it's hard for me to do this on the fly. But anyway, what we're going to have here, this is going to become 3/2, plugging in 1 over square root of 2 here. This is going to become 1/2 to the 1/3. And then here, minus 3/8. And then this is going to become 1/2. 4/3. You know what I think I'll do? Let's split that up. I can write that as u half to the 1/3 times 3 over 3 and just have a u squared, just have like a 1/2 here. Because that's going to be like 3 over 3 plus 1 over 3, 4 over 3. And then I can factor this thing out. So then let's just see if we can add all this stuff together and make enough space. I probably should have conserved my space better, but see, this is what happens when you're doing, we're trying to do a live video. So 3/2 minus 3/8 here, this is going to be, I can write that as 12 over 8 minus 3 over 8, which is going to be 9 over 8. And then here I wanted to factor out a minus 1/2 to the 1/3, kind of like this. And here I think I'll factor out a 3/8. So let's see what happens when I do that. That's going to leave the first term as just a 4. And then I think we're going to have minus 1/2 here because this stuff goes away. So hard to follow, but yeah, sorry, that's all what's going on there. Then trying to put this all together, we have the cube root of 2, 3/8, and then I can write this as 8 over 2, so this is going to become 7 over 2. And yeah, there's a whole bunch of different ways we could simplify this, but I think what I want to do is just leave it 9/8 minus 1 over cubed root of 2. Multiplying this together, we get 21 over 16, and I'll just circle it. So this is a never-ending dilemma because then I might want to factor out an 8. Like I could factor this 20 different ways, and we could be here all day, but it's just not worth it. So Let's move on to number 7. Okay, number 7, we're integrating from 0 to pi over 2 of this whole mess. Let's see, this is going to be 2x squared over 2 factorial. Now I'm hoping I can remember this formula because I'm not sure if I can remember it exactly the way it is. So, okay, let me just write all this stuff down. It's kind of a long series here. So you can kind of see where it's going. We got all even factorials here in the denominator. And I think this goes on forever, right? Yeah, this is infinite. But then at the end, they have a sine x, and of course they have a dx right there. And now the thing we need to notice, what's happening here is this is really similar to the power series for cosine, but the thing is they've inputted here 2x. So this isn't really cosine x, this is a very similar to cosine 2x. But then if you actually looked at the formula, they've reversed the sign, because I think the way it should go is, let's see, I see this one should be a negative. I think it should be, let me just see if I can make sense of it in my mind. Yeah, so like this one should be like, so they've reversed the sign on cosine 2x, and they've removed this first term, which would be, oh, but see, this is an x to the 0, so this term's 1. So they reversed the sign and removed a 1, so this whole thing is going to be 1 minus cosine 2x. So if that's the case, all we need to do, if this is 1 minus cosine 2x, this isn't too bad. I can just we have sine x here. I can just distribute this in and rewrite it. So what's going to happen when I do that? We're integrating 0 to pi over 2 sine x dx, distribute in minus sine, and then what happens? This becomes cosine 2x sine x. And there's a few ways to do this here, but I think what I'm going to do for this is let's just write this as 2 cosine squared x using the double angle formula like this to set up a u substitution. Then when I do that, if we distribute in sine x again, I don't know if this is the most efficient way, but you'll notice minus times minus plus gives me another integral with sine x, which is the same as this right here. So what I can do is just make this 2 copies right here and cancel this off right here. So then let's just deal with this one, because we can just integrate this. So the integral of sine x is going to be minus cosine x. We have minus 2 cosine x evaluated from 0 to pi over 2. And then here for the second one, we're going to have this going to be integral, just to clean it up. Well, this integral, but this is going to be now cosine squared x sine x. And what I want to do here is a u substitution. I'll make u equal to cosine x, so then du is going to be minus sine x dx. Create a minus here, bring a minus up front, and this becomes a plus. So then before I do that, let's evaluate over here. So plugging in pi over 2, the first term, cosine of pi over 2 is 0. Second term, minus times minus is plus, so we're going to have here plus 2. Cosine 0, just a 1. Okay, good. Then here we're going to have plus 2. Integrating here, let's kind of do this on the fly, right? So this has become u squared, and this is du. So when I integrate this, but yeah, I actually have to update my balance. All right, let me write it up then, sorry. So updating our balance, plugging that in here, cosine pi over 2 is 0, cosine 0 is 1, and now we have u squared du. I'll just reverse this to make it 0 to 1, and then we'll make this a minus sign, right? So then coming over here, make a little space. We're just going to have 2 minus 2. Integral is going to be u cubed over 3, evaluated from 0 to 1. The 0 is just going to be 0, so we plug in a 1. We're going to have 2 minus 2 1/3. That's going to be, we can reduce that to 6/3 minus 2/3. And so for this one, we get 4/3. Okay, that one was a little bit of work. So I think I'm almost halfway there. Moving on to number 8. What do we have for number 8? Number 8. Oh, the other thing is my papers are all out of order, right? So it's like I've got the added challenge of actually trying to find the problems and hoping I can read my handwriting and keep the board from flying off the table, all that kind of stuff. So, yeah, seriously, these are all out of order. So, number 8. For 8, we've got the integral of dx over 4 plus 9x squared. Need some more water. Okay, good. Okay, so this is clearly like our arctan situation. So this one's not bad, but we just have to deal with these constants here, 4 and 9. You could probably remember a formula for this case, but I actually don't remember how to do it that way. So I just kind of do it out. And what I'll do is I'll factor a 9 out of this. So if we do that, if I factor a 9 out of everything, I'll bring a 1/9 in front. Then doing that, this here is going to become 4/9. But what I'll do over here is I'll write it as 2/3 squared. Then this just becomes a 1, so we have an x squared here. And then for this, we just have our arctan formula. So we're basically going right to a solution of 1/9 in front. We have like, this is our a value in the formula, but we need to flip it. So we'll have a 3/2 here. Then arctan, do the same thing, flip the a again with the x. And so we're going to end up here. This is going to become 3/2 x. But then to simplify it, we can cancel 3 and 9 here. Multiply it together, we get a solution 1/6 arctan 3/2 x plus c. See, that's, I need it to look better than that, come on. Okay, put a plus c on there, and there we go. Okay, so moving on to number 9. Okay, this one doesn't look too bad, I don't think. Number 9, I don't know if this is going to be partial fractions, or can I, let's see. So it's going to be dx over x squared plus 5x plus 6. Okay, well this thing can definitely easily be factored. I can factor this as x plus 3 times x plus 2. Oh, and I kind of like to avoid partial fractions. So what we can kind of do is do this on the fly. We've got a 1 in the numerator. These different ways don't save that much time. It's like, it's not a big deal to me, but this is kind of the way I like to do it. So we don't have to do the partial fractions, even though I'm saving like 1 second. It doesn't really matter. But I can create the 1 like this. The reason I do that is because then the x's are going to cancel, right? So the x's are going to cancel. 3 minus 2 is 1. So this whole thing is just 1. So then when I split this off into 2 integrals, we get cancellation. And that's really why I'm doing it, right? Just to cancel it off so we don't have to deal with it. So we do it like this, minus sign between these, x plus 2 here, right? And then we'll have there's going to be a dx in there somewhere, right? So then when we do this, the x plus 3's cancel here, we have a 1 there. X plus 2's cancel, we have a 1 there. Integrate the first one, just integrating x plus 2 in the denominator. That's going to be natural log x plus 2, absolute value, minus this one, just have an x plus 3, natural log x plus 3. You can put these together with log properties. I'm just going to leave it at a plus c, and we're on to number 10. Okay, number 10, this is quick, but it's kind of a good one. So we have the integral of cosine x times tangent x over x sine x all squared dx. Okay, at first it looks a little It looks kind of confusing because there's so many different trig functions, but this right here is the same thing as cotangent. We're multiplying it times tangent. Just to write that out, we can just put it back, right? Cosine x over sine x times sine x over cos x, and then you cancel this, and this whole thing is just 1. So what we're really doing is we're just integrating 1 over x squared dx. You integrate that and you get minus 1 over x plus c. Okay, I wonder if I can fit another problem in so I don't have to erase the board every time, right? No, this one's not gonna fit in there though, so I'm gonna erase it. It's a good goal to shoot for though, for at some point, to try to get two on the same board. Number 11, what's happening? Let's see if I can read this. So we've got the integral of dx over the square root of the square root of x minus 1. Okay. I think what I want to do, what needs to happen is, let's do a u substitution here, because if that's u, then this is going to be, the denominator is going to be simple. We'll need a value for x. Let's see how this is going to work. So we'll say u square root of x minus 1. Then we can rearrange this. Square root of x equals u plus 1. Square both sides. X equals u squared plus 2u plus 1. Take a derivative for the dx value, then dx is going to be just 2u plus 2 du. Okay, so then let's just do this and see what happens. This is our dx, so we have 2u. I think this is going to be good. 2u plus 2 du. This is just going to be square root of u. I'll write this as u 1/2. Then just divide it in. So then break it up. This is going to be 2u 1/2, and then this is going to be plus 2u minus 1/2. So then integrate it. We're going to have 2. This is going to become u 3/2. Bring out 2/3 reciprocal here. Then plus 2. This with power rule u 1/2. Then bring a 2 times this 2. We have a 4 here. Then I think before I back substitute, you know what I can do? Let's factor out like this term. So if I factor out 4u, I write like this. I'll factor that out. Then this just becomes 1/3. This just becomes u over 3, and this is just plus 1 here. So then when we back substitute here with our u, like all the way back substitute, then this is going to become, this becomes like our original expression. This becomes 4 square root of x minus 1. Then here, oh, I see, you know, I do need another simplification, I think. You know what we need to do for this plus 1 here? I'm going to write this as 3 over 3. Just so I can, we could leave it, but let's just simplify it a little bit more. I think I need to. Yeah, let's just do that. Okay, so then what I can do is let's actually factor out this 3. Okay, I'll bring this right here. And then let's see if I can put it all together. So we're going to have 4/3 square root x minus 1. And then here, now we have left with just square root of x. 3 minus 1 or plus 2. Add a plus c on there, and that's going to do it. Okay, moving on to number 12. I'll tell you, doing a lot of integrals is pretty tiring. I mean, doesn't seem like much, but I don't know, just does kind of like wear you down a little bit. So, number 12. Integral of x dx over 1 plus x to the 4th. Okay, I think this is an easy one. What I want to do is, let's take this x to the 4th here. And what I can do is, I can write this as x squared. And then if I do a u substitution, it's going to work well with this. So I'll set u equal to x squared. Du equals 2x dx. I'll just multiply in a 2 right here. So that way we have this exactly, but I don't want to change it, so I'll multiply by 1/2 right there. So then go ahead, let's just substitute. Let's just do this thing right here. So I've got my 1/2 here. This is du, and then this becomes just 1 plus u squared. This, of course, is arctan, so this is nice. So this is going to become arctan of u over 2. Back substitute it, and this is going to be, for the solution, just arctan x squared over 2 plus c, and circle it. Okay, so what's next? 13. See, if I would have saved a little space, maybe I could have got 13 in here. Where's 13 now? 13. Oh shoot, am I missing 13? This is gonna mess up the whole thing if I'm missing a problem. Oh. You know what, I can fit this one in. Okay, so 13. This is gonna be the integral from minus pi to pi of x cubed cosine x sine to the 4th x dx. Okay, what I want to do here, it's about the odd and even functions. This right here is even. This right here, sine is odd, but because it's to the 4th power, this right here is even. When you do this, you can kind of almost like cancel off the even functions, because when you think about plugging in a minus x, the minus sign is just going to go away, and so everything here is not really contributing to what's happening, and this is an odd function. So the whole thing is an odd function. We have that principle that for finite bounds minus a to a, f of x is odd, then the integral is just 0. And that's it. You can pretty much just do this in like 1 second and write down the answer of 0. Okay, moving on to 14. Now that my papers are all ordered to find that one. See, I really could have done a better job with this part, right? Because I knew I was going to need to find the problems, and I just kind of randomly had them written all over the place. Let's see, I found 15, 18. Ah, there we go, 14. This is kind of a pain. Okay. 14, this is just going to be natural log x cubed dx. I think what I want to do for this is I kind of want to work this a different way. So first of all, we know I'm going to do for ln x dx. For this one, I'm going to assume we know the formula for this, that this integral is just x ln x minus x. Now the other thing I'm going to want to use is the integral. We're going to need this one. We basically need all three. Ln x, we need ln x cubed. And maybe there's a better way, I don't know, but this is the way I do it. So for this, I'm going to need this in order to do this. Let's just do integration by parts over here on this one. So we just do the standard thing. We kind of just create a 1, and we'll do our di table. So integrating here, we get an x. Integral here, we got first power rule, 2 ln x. And then chain rule, but then that's going to create a 1 over x, which we can use to cancel with that. So for this, we have part of it right here. Okay, we have x ln x all squared. Then here we're going to have an integral, but what's going to happen, we're going to have minus 2. The x's are going to cancel, and we have, get rid of that. The x's are going to cancel, and then here we're going to have the integral of ln x, but we already have our answer for that right there. So that's kind of why I went in this order, because I wanted that value, so I can just take that, plug it in here, this x ln x minus x, okay? So then let's just clean this up really quick. So this full solution for this is going to be this thing, distribute this in, we get minus 2x no, just 1x. Minus 2x ln x minus 2 times minus x plus 2x. So then coming to our goal, this thing, again, integration by parts, but now we're set up as we've got these two values. So integration by parts, we do DI method, we create a 1, integrate a 1, and then really similar to what we just did on this one, we first use power rule, so we're going to have 3 ln x squared. Derivative of this is going to be 1 over x. Here, integral of this is 1 over x. So then for this, we have part of our solution here, which is going to be x ln x all cubed. Who knows if I have enough space up there. But then for this integral here, we have minus 3. The x's cancel, and then we have just the integral of ln x squared. Well, we have that right here. So I need to distribute in, let's just do it on the fly, distribute minus 3 into this. We get minus 3x ln x all squared. Minus 3 times this gives me plus 6x ln x. Minus 3 times this, minus 6x plus c, and that's it. That's it, right? Okay, so that's 14. I think I had 15 ready somewhere. Where's 15? Okay, 15. 15 is more with natural log. A little something different, but it's still natural log. I think, oh, you know, I think I've done something really similar to this one in the past. Okay, so what we have here for 15 is we're going to have the integral of 1 over ln x minus 1 over ln x all squared. The interesting thing here, when I was first looking at it, I mean, of course you could, well, I don't know what would happen if you broke into two integrals. That might not be that fun. So let's not talk about that. Let's push that aside. But the minus sign, it makes you think of the, like the reverse product rule, that maybe like there's a relationship with the derivatives. I don't know, I don't really want to deal with that either. I think what I want to do is get a common denominator here. If I multiply in an ln x here to get a common denominator and multiply it here, then what happens is the numerator becomes ln x minus 1 all over ln x squared. But then what happens here is this looks exactly like the quotient rule. So then just kind of going with that, for the quotient rule, let's look at it really quick. Just like assuming we have two different functions in x, f over g, take the derivative, it's going to be this thing. And the thing that clues you in is just the bottom term squared. So if this is going to work, we're saying this is going to be g. So we're saying g is ln x. And we're going to need g prime. So g prime is 1 over x. And what we need to do is we really need this, we want to know what f is. We can kind of focus in on any part. Like I can just kind of look at like, okay, we're saying I want fg prime. If this is going to work, fg prime needs to be 1. So we already know our g prime. So we're saying f times 1 over x needs to be 1. What's going to work? Well, we need f to be x. So we're saying f equals x. Then take a derivative here, f prime is going to be 1. Then we can just check it to make sure everything works. Like we already did this, fg prime, x times 1 over x gives me this 1. That's good. You know, we know this, right? G squared, that works. Here we want to say f prime g needs to be equal to ln x. So then we're saying 1 times ln x equals ln x. That's a check, so that's good. So what we're saying, coming back, because what's happening is this whole thing, this reverse quotient rule is inside the integral. A derivative inside the integral, so our solution is going to be in this form, f over g plus c. We just grab this and this. And so for the solution of this, we get our f over g, so it's going to be x over ln x plus c. Doesn't really need parentheses. But there you go. So circle it. And going on to 16. So let's see, I got 3 left. I think I can make it, I'm not sure. Oh, I'm gonna have to check the time too though, right? Because I think there's like a 45-minute time limit on this. I think that's what SwinBee gives you, so I don't know if I'm gonna make it. Anything after 45 minutes doesn't count. Oh, I don't really want to. Okay, 16. Oh, this isn't that bad. Okay, wait. 16, this is going to be e minus 2x cosine 3x dx. I think the garbage truck is back. That's not right. We already had garbage. Oh, come on. Okay, so for this one, this is just going to be integration by parts. I feel almost like I should do this with the using complex numbers, but I don't really feel like it. So we're just going to do integration by parts right here. I think what I'll do is we'll differentiate this. So we'll differentiate cosine 3x, integrate e minus 2x. Derivative here, this is going to be minus sine 3x, bring a 3 out, right? Then here, integral here, e minus 2x over 2, bring a minus sign. Then we'll do this one more time. So this one, integral of sine 3x is going to be cosine 3x, bring out another 3, we have a minus 9 here. Then doing this again, we get another minus sign that's going to cancel with this one. So this is just going to become e minus 2x over 4. Now when we do this, we have part of the solution on the diagonal. But then with this last one, we basically get our integral back just with some constant values, right? We're going to have to deal with this. So when I do this, let's see, I think what I'll do, let's factor out, I'm going to factor out e minus 2x over 4. Yeah, let's do it like that. And then what's going to happen is this one's going to be positive. Yeah, so then we'll have, this is going to become 3 sine 3x. This one's going to be a negative. But we have this 2, so this is going to become 1/2 cosine 3x. I know I'm forgetting something. I pulled out a 4. Oh, actually, sorry. If I factor out a 4, this needs to be a 2, right? Because doing that, minus 2 over 4 gives me this minus 1/2. This one, yeah, that works. Okay. And then dealing with this last thing here, as an integral, we have this minus 9 over 4. So I'm going to have minus 9 over 4. This thing, which is our original integral, which I'll call I. So this thing's going to be minus 9/4 I. To get rid of this, we'll add 9/4 I, 9 over 4 I on both sides, right? I can look at this as 4 over 4 I. So on the left side, we end up with 13 over 4 I equal to this whole thing here, which I'll just kind of copy down really quick. But let's make some more space over here. Probably should just did it lower, but anyway. We have this thing here, 3 sine 3x minus 2 cosine 3x. Kind of do it like this. Then what I need to do to isolate our solution, multiply by 4 over 13 on both sides. Multiply by 4 over 13 here. This cancels. So we're just, this whole thing's just going to be our answer. But I can cancel the 4s. And I think to try to make it look nice, right, for like the thumbnail or whatever. Well, not really the thumbnail, but let's just clean it up. And we'll put a 13 here. Add a plus C and circle it. Okay, moving on, number 17. We got 2 left. Get badly winded here. You need like some training for a lot of integrals. Oh, 17, okay. This one's kind of funny. Like there's like certain go-tos in all the integration bees that like you kind of see over and over again. It's like there's a certain playbook for integration bee writers, and this is one pretty easy one that comes up a lot. Let's see if I can copy it down right. So 17, we have sine x times cosine of cosine x. See, you know this, like you've seen this a million times, right? Or at least like, maybe not 1 million, but like 1,000 times you've seen it, I think. So what we have here is this kind of embedded thing that's confusing to look at. Now, there's kind of a slow, careful way where we see that, you know, we go to the innermost thing and we could definitely do a u substitution for cosine x, and we've got a sine here, so that would work fine. But when it's embedded more than once, I would definitely like to save a step. And so that's telling me, don't do the u substitution for cosine x, try to save a step, do it for this. There's another way where you could try to like get all of it at once, but that's a little too, like I don't want to do it where it's like we can see the future. Like I don't want to pretend like we can always see. I mean, we could do every integral where we just write down the answer, but that's not much of a video. So what I'm going to do is we'll do the u substitution here for this. So we'll say u equals sine cosine x, take a derivative. Derivative of this is going to be cosine of cosine x. Chain rule, derivative of that gives me a minus sine x dx. So then what we have here, that's going to be really similar to this plus our dx. We just have that minus sign. So let me create the minus sign here, and I'll create another minus sign here so I'm not changing it. And so we'll just go ahead with this thing. So then we got a whole bunch of stuff that's going to be du. The integral is going to reduce, because this is our u, the whole integral is just going to reduce down to minus sine u du. Integral of minus sine u, that's just going to be cosine u. Back substitute with this thing to finish it, and we end up with cosine of sine of cosine x, add a plus c, and there you have it, 17. So, right, okay, that's good. Okay, last problem, 18, if I can find it. Where did 18 go? Okay, 18. 18 is not too bad. Okay, 18, we're gonna have just x squared natural log x dx. Okay, I think we had a lot of natural logs in this one, and I think every time pretty much we had to do integration by parts. So let's do integration by parts again on this. DI method, I want to differentiate this. So we're going to differentiate natural log x and integrate this thing. So we're integrating x squared. Derivative here, this is going to be minus 1 over x. Integral here, x cubed over 3. See, when you get tired, you can't even, it's like your 3's start looking like that. No one wants that. So, but still what we can do is we can copy down part of the solution here. So this is going to become x cubed over 3 natural log x. This last thing here is going to be an integral, so we'll have a minus 1/3 in front, but we can cancel an x with an x cubed, so this is just going to become x squared dx here. And then I think we can just finish this off. So we're going to have this, we'll just bring down this first part, right? Then here we integrate this, we're going to have x cubed over 1/3. Multiplying the third times this, we're going to have minus 1 over 9 x cubed, add a plus c, and that's it. Okay, there you have it. All 18 problems from SwinBee 2022. Thanks everyone for watching. Have a good day.